Okay, welcome everybody to today's class, day 2 on linear regression. Hopefully we'll have more people trickling in, but let's get started since it's already after 12:25. Okay, so today we're going to be... Okay, welcome everybody to today's class, day 2 on linear regression. Hopefully we'll have people trickling in, but let's get started since it's already after 12:25. Okay, so today we're going to be... Okay. Sorry about that. The YouTube stream open, and that was a bad idea. Okay, so sorry. Hopefully everybody can hear me.
Yep.
Okay, good. So here we go. We're going to be talking a little bit today about overfitting, model generalizability, and the bias variance trade-off. A little bit about cross-validation, which we'll discuss in even more detail later into the course, but we'll get a feeling for it today. And we'll think about using categorical variables for regression. So if you haven't read the Introduction to Statistical Learning, Chapter 3, check that out. And let's just start with a quick recap from our last lecture where we introduced simple linear regression. So the idea here, we have in sample points, X and Y, we think of X as the explanatory variable or the predictor variable or the dependent variable, lots of different names for it. And Y is the response variable, and we want to model a linear relationship where we're predicting Y as a linear function of X. Okay, and so as we saw, a lot of times data doesn't perfectly fit a line, but we defined a way to measure the goodness of fit of a line through data, and then that least squares idea of best fit, we defined optimal parameters beta 0 hat, the best intercept, and beta 1 hat, the best slope that best fits the data in the least squares sense. Okay, and so we had a theorem giving exact formulas for the slope and the intercept. Of course, and we're going to be computing these using, so you don't actually have to do these formulas by hand. And then we generalized the concept to multilinear regression. So in this case, we're still thinking about a linear relationship between the predictors and the response variable, but we may have more than one X. So say we have M X's, so we could think of these as M different features or variables that we have observed, all of which we're trying to use to predict Y. Okay, and then we also talked a little bit at the end of class about nonlinear relationships. This general framework is actually very powerful, and so we could think about replacing x1 with any kind of function of the variables. So here we could think of modeling y as some intercept plus coefficient beta 1 times some nonlinear function of the variables, right? This could be x1 squared, or it could be x1 times x2, or sine of x1, or e to the x1, right? So this could be really anything. But if we kind of define new variables as nonlinear functions of the original variables, then the mathematical framework for computing these optimal coefficients the same. We're still just solving a linear regression problem on these new variables. Okay, and doing regression in Python, you've got several different options. Stats models is really nice for all of the statistical functionality. Scikit-learn is really nice for cross-validation and things on the machine learning side, which we'll be discussing some today. And also, like I think I mentioned briefly last time, SciPy has some regression functionality, but not a ton. Okay, so first of all, we'll just do our standard imports. like we do every lecture for the most part, variations. And then last time we were looking at the advertising data set where we had 200 different markets. You can think of those cities, and then we were predicting sales from 3 possible variables, which was TV, radio, and newspaper. And you may remember that after some exploring and experimenting, we ended up with a very good model where we used 2 of the variables, TV and radio. Newspaper was not helpful. And we also incorporated this nonlinear term, which was the interaction between TV and radio. And that was actually very helpful for the model to have this interaction term in there. And so in summary, this was the model that we ran using the OLS function and stats models, and we got an R² value of 97. In addition, saw that all of the coefficients were significant here. Okay. And also, so you remember, you want to look at the p-values for your individual coefficients, TV, radio, interaction, and you may also want to look at the p-value up here for your f-test, and that's just the test that at least one of the coefficients in the model is non-zero. Doesn't mean all of them are, but at least one of them is. There is at least some type of significant relationship. Okay, and then the other thing that you want to remember about the output, in addition to looking at the R² value and in addition looking to the p-values, is how to interpret the slopes. Yeah, first of all, you write down the equation of the line using the coefficients. So here we would say y equals 6.7 plus 0.019 times TV plus 0.028 times radio plus 0.001 times TV times radio. And how would we interpret this? For example, if we spend an extra $1,000 on TV, we'll sell another 19 units. If we spend an extra $1,000 on radio, we'll sell another 29 units. So seems like it makes sense to spend more on radio. Okay, and then also very useful sometimes to plot and visualize the data. And that's kind of what we did last time. First, initializing the 3D figure axis, and then adding the scatter plot of the data, and then creating a surface plot of the predicted values by just creating a grid of values for the x's, and then applying the predicted relationship as calculated by the regression software, right? This is stored in the output, ADNL.params. So that's where the coefficients get stored. We can use those to explicitly plot the surface and get this little picture here where you can see it's not a flat surface anymore, but it's really fitting the data very well. Okay, so that was mainly just to kind of recap from last time. Were there any questions related to that or the material from last time? Okay.
Can you remind me what capital R² meant?
Oh yeah, good question. So how do we capital R²? So the way you want to say it is that the model accounts for 97%, think of it as a percent, the model accounts for 97% of the variation in Y, in the response variable, which is a lot, right? So 97% of the variation in Y is explained by the model. And we saw when you're just doing simple linear regression, so 1x and 1y, then this capital R² is the same thing as the little r², which is just the the linear correlation coefficient between y and the predicted y hats according to the model. But this is a more general way of making the interpretation, which we'll want to keep with us as we develop more complicated models.
Thank you.
Yeah, no problem. Any other questions? Okay, well, feel free to, put them in the chat or any. Let's continue to move on now. So, okay, right. So what we saw last time was that by using more variables and also incorporating this interaction, we got a lot better model. We improved our R-squared value. So it's tempting to keep adding in, more variables, more predictors, get a better and better fit. But this can be quite problematic. We want models that generalize really well beyond the data that we're building them on. And so we want to be careful not to owe to the data when we're building our model. Okay, so let's talk a little bit about overfitting, underfitting, and model generalizability, which is related to something called the bias variance trade-off. So here's the basic idea. What's our goal? Our goal is to develop a model that will perform well, not only on the data set that we use to build it, but on similar data. Let's say we go out and we do another study, we collect another sample. Do we see the same relationship? And if a model satisfies this criterion, we say that it is generalizable. So for example, think about this real baby toy model where we have these black points and we want to build a model to predict. We could, of course, just do a linear model like we discussed last time. That's the black line. Or we could build a more complicated model. Let's say we want to fit a higher order polynomial. We could do that, and we could perfectly fit a polynomial, a higher order polynomial that goes through all of these points. Okay, so on this data set, and the blue model and the black model respectively, on this data set, the blue model fits perfectly. You would have zero error, right? You would have like a perfect R-squared. But you can see the problem if you get a new data point coming in. Maybe we get a new data point coming in here, which seems quite reasonable based on the trend. It's going to be really far from its predicted value up there on the blue curve. On the other hand, the black line is, far from some of these points, but it looks like it'll generalize really well. As new data points come in, it's not going to be a disaster. They shouldn't be too far from the line. Okay, so we would call this the training data set. But what we want to do is we want to test our model on a testing data set that's independent from the training data set. And so we see here, for example, we expect blue to do really well on the training data set, but very poorly on the test data set. And on the other hand, the black model to do not as well on the training data set, but well on the test data set. Okay, and so there's a trade-off going on here, so which model is better? What we want to do is build a model that's complex enough to fit the data, that's not too simple, but that's not so complex that it doesn't generalize well. And this phenomenon is called the bias trade-off. So we can think of decomposing our error into three terms. So the error consists of bias plus variance plus irreducible error. And so the bias of the method is error that arises because the model you use is not complicated enough to actually fit the data. So maybe you're making too many simplifying assumptions and your data is not, for example, you're computing a linear regression, but your data is nonlinear. There's a bias there. The variance of the method is how much the model will change based on the sample data. So this is about the generalizability to a test data set. So if the variance is very large, then it won't do well on the test data set. And then the irreducible error, you really can't think about generally. So that's kind of error in the data itself, which you can't really do anything about in terms of model. So basically, we're concerned about balancing these two terms, balancing the bias and the variance. Okay. Okay, so black line, high bias, low variance, blue, low bias, high variance. How do we balance these things? Okay, and because remember that your data can be noisy, and of course it's hard to know sometimes a priori the degree of the noise, but generally, it's a sort of common assumption occurrence. So let's think about generalizability in practice. And we're going to look at the auto data set, which contains 9 features: miles per gallon, cylinders, displacement, horsepower, weight, acceleration, year, origin, name, for 397 different used cars. So first we'll read in the data, and what you will notice if you print the data type data frame is that horsepower imported as an object, which it shouldn't have. Power is a number, should be an integer, but it imported as an object. That's because there are a couple of question marks in the data set, a couple of missing values. So we can clean this up by specifically removing the question marks and then mapping the remaining horsepower values to integers. And once we do that, we get this nice and correctly formatted data frame. Okay, and then remember, you can use the .describe function to
Does
get...
that function remove the entire line with a question mark?
Oh, this one here? Yes. This removes all lines that have a question mark in the horsepower field. Because this says data frame auto is equal to data frame auto restricted to the rows where horsepower is not equal to question mark. So you could call this a new data frame, but since we really don't want the old one, we'll just call it auto. So this will be smaller than what it originally was. I think there's only like maybe 2 question marks or something, not a ton. Okay, so you can use the describe function to get your numerical summaries. Let's focus on the relationship between miles per gallon and horsepower, because it's got a slightly more complicated relationship than some of the data we were looking at last lecture. Definitely looks like we've got some curvature here. So here we're just plotting the horsepower versus the miles per gallon. And we see this kind of, some noise, but definitely a strong shift between the variables. So let's consider generalizing beyond just simple linear regression. Let's think about doing higher order polynomials. So we'll consider the model. Here it says linear model. It's a little confusing because it's linear in these variables, but because these variables are powers of horsepower, it actually is a nonlinear model for the data. It's going to be modeling it as various polynomials, second degree, third degree, fourth degree, etc., up through an nth degree polynomial. Okay, so it might seem that choosing m to be large would be a good thing, right? We could maybe really fit the data with a high degree polynomial since it's more flexible. But let's actually try it empirically and see how it goes. So we're going to fit a number of different polynomial models here. So linear, and then this is another thing you can do with the OLS function. This is a syntax that we didn't use last time. We don't actually have this horsepower squared variable saved in our data frame, but you can use this syntax to tell it to use horsepower squared as another variable, and then here horsepower squared plus horsepower cubed, and then here in addition horsepower to the fourth. Okay, so we run the linear regression for all 4 of these models.
Quick
and
question.
Then go ahead.
So we wouldn't be able to do, for example, on MR2, we wouldn't be able to say horsepower plus horsepower squared. We have to use this like I notation.
Yes.
Okay.
Yes, yes, I think that just sort of tells Python that, you know, this is not a variable name in and of itself.
I gotcha.
We're doing some kind of like function of the variable. But you know, here you could change this up. You could probably make this like sine of horsepower.
Got it. No, that makes sense.
Horsepower.
Thank you.
Yeah.
Why are you using a float for the power?
I don't think there's any reason that it needs to be a float. I would think it could be an integer as well. Yeah, yeah, you can use an integer. So I don't think there's a reason to use a float here. Okay, let's see. Okay, so yeah, take a look at the pictures. So here we are making a set of the data, and then we saved all of the parameter outputs of the models in these little dictionaries, and now we can create a grid of X values, and then for each model we can evaluate the model on the grid by creating the equation from the parameters. So that's all we're doing here for the 4 models, and then we can and you can see here's our data, and then you can see the linear fit, and then the orange one is the second degree, the green one is the third degree. Those second and third degree ones look pretty close to each other. The fourth degree starts to veer off a little bit. So here it can be a little useful to kind of plot these models a little bit beyond the range of the data and kind of see what the model does as you leave the range of data. Okay, and then if we look at the R-squared values that go along with these fits, for the linear model, you get an R-squared of 60.5%. So the linear model can account for 60.5% of the variation in miles per gallon. And then the second degree polynomial can account for 68.8%, and then 68.8, again, 68.9. So what we see is kind of a big jump in R-squared values from the first degree to the second degree model, but after that, it really doesn't change a whole lot by increasing the complexity. And you can prove, actually it's always true, that adding in another variable never make your R-squared worse. So because when we're building these models, we're just adding in more information, the R-squared can never go down. Okay, but that doesn't mean that these are, that it, as we've discussed, that doesn't mean that it's good to keep adding in variables. We want to not overfit the data. And so you can see, if you take a look at this 4th degree polynomial fit that has the R squared of 0.69, that the p-values for the coefficients are very, very high, right? So this is not looking to be a good model. We're 7 significant coefficients. Okay, so we could rely on Occam's razor to sort of decide between the models. We could look at how the R squared changes and say, well, we gain much by increasing after 2, so let's do a second, but we do see a good increase by going from a 1st degree to a 2nd degree polynomial, so let's go with the 2nd degree. And that is, a reasonable way of thinking for sure, but there is an even better or more scientific way to decide between various models using a procedure called cross-validation. So cross-validation is a clever method for developing generalizable models that aren't underfit or overfit. And so it's a general method for assessing how the results of a predictive model, like regression or classification, will generalize to an independent data set. Okay, so in this context, where we're looking at regression, it's a method for assessing how well the regression model will generalize to data points that weren't used to train the models. Okay, and the idea is actually very simple. You're going to split the data into 2 groups, make it a training data set and a testing data set. Then you're going to train a lot of different competing models on the training data set. Okay, so you could try 1st degree polynomials, 2nd, 3rd, 4th, 5th. You could try exponential. You could, do all kinds of fun things, fit as many you want on the training data set, then test the accuracy of each one on the testing data set, and compare the accuracies on the testing data set to determine which best. Because that's really what you care about. You really don't care about its performance on the training data set. You only care about its performance on the testing data set. Okay, so this is a simple but actually very powerful idea, and it's really, it's kind of created a new way of thinking about things in machine learning and in data analysis. And of course, you have to decide how to split the data into groups. Like, well, should you just split it in half? Should you use most of your data for training? Should you use most of your data for testing? What people actually like to do in practice is repeat this procedure. So sometimes they'll divide the data set in one way, using a certain portion of it for training and testing, and then they'll change the split and kind of repeat this training test experiment over different splits of the data. And we'll talk about that some more in a later lecture, but let's just kind of have this idea of a training data set where we construct models, and a testing data set where we evaluate them. Okay, so as the model becomes more complex, as M increases, the accuracy always increases for the training data set, but at some point it starts to overfit the data, and the accuracy will decrease for the test data set. And so cross-validation allows us to find the sweet spot, or how do we pick, for example, that parameter M in this example on the auto data set. Okay, and so let's see, let's take a look specifically at the data set and see how we can use the cross-validation functionality in the scikit-learn package in order to select the best model. Okay, so first we can sort of initialize a linear regression object. And then, and so in some ways, the scikit is not quite as user-friendly as the stats model OLS. Here we have to actually explicitly add in the columns into the data set that we want to consider. So here we're actually explicitly adding in these horsepower columns, horsepower, squared, cubed, etc. And then also it doesn't play very well with the pandas data frame. So we have to extract the values from the pandas data frame before we feed it into the linear regression function. Last lecture, when we just had one variable, one explanatory variable, one X value, we also had to do a reshape here. So we did like dot values dot reshape here, because you have, I think, more than one, it somehow comes out, the syntax, comes out right automatically. Be aware of that. You may need to do a reshape depending on the dimensions. And so you can see what it looks like if we let X be the relevant columns which correspond to the various powers of horsepower. Then it should look like this when you print it. So this, and if you take a look at what kind of data type it is, it's saying it's a NumPy array. So that should be the format that you feed into the linear regression function. Okay, and then same for Y. So we can take a look, we can plot this, and then what this code is doing, it's kind of, repeating what we were doing before, but in scikit-learn. So just so you can kind of see the syntax here, make a grid of values, and then you're just defining the powers on that grid. And then for each model, you're fitting the model, and then you're plotting the prediction on that grid of values that you defined. And so here we see our lovely models. Here we also have the fifth power one, which, yeah. Okay, so now, actually, well, let me see how much more we want to, yeah, let's go through this and then we'll take our break. I don't think that'll take long. So now let's see specifically how we can do cross-validation. So in scikit-learn, you can use the train test split function to split the data set into a training data set and a test data set. The score function returns the coefficient of determination, R squared, of the prediction. Okay, so this is really handy because it can do this process automatically for you. And so in this code, the data is split in a bit of an unusual way. The test data set is 90%, and the training data set is only 10%. Usually, I'll just say, usually you make the training more than half of your data and the testing data set less than half of your, kind of reversed just to illustrate the overfitting point that we want to make in this lecture. Okay, so we want to import this train test split function, and then, so we're going to input our X's, we're going to input our Y's, and we're going to say we want the test to be 90% of the data. And then we're going to output this X train, X test, Y train, Y test. And you can take a look here at what you're getting. And then we're going to take a look at the plot. Here, the black points are the testing data set and the red points are the training data set. And then seeing also again here the different models constructed on the training data set. Okay, and so so here I mean, and I guess I will say it's not like it's doing all of this for you. It's split the data for you, but you're still kind of going through this process of, looping through the models and sort of doing this evaluation, fitting the training data, right? So you're looping through the models, you're fitting the model on the training data, and then you're scoring the model on the testing, well, both on the training and the testing data set. But all you really care about is the score on the testing data set. And so you can see what you're getting here. As you increase the complexity of the model, of course, the score on the training data set just goes up and up until it kind of plateaus, but it never decreases. But you can see here on the testing data set, the performance increases from 1 to 2, and then actually it decreases from 2 to 3 and 3 to 4, etc. So here, this is kind of nice because instead of playing the guessing game about, okay, well, where does the R squared value plateau, we can actually just look for the highest value on the test data set and say, it looks like the second degree polynomial model is really the best model. Okay. All right, so that's basically that we want to play. So we want to find a model sufficiently complex to describe the training data, but not so complex that it isn't generalizable to new data, and cross-validation is a great way to do that. Okay, so let's take our 5-minute break, and then we'll come back and I'll go over a few more things related to the data set that you're going to be looking at for your activity today. And then we will do our breakout groups in a little bit. So it's 1:03, so let's come back at 1:08. All right.
I have a super quick question.
Yeah, sure, go for it.
I just wanted to clarify something versus the training and testing data set. So you take all the data values that you were given and you split them into 2 groups. So you only create your linear regression model on, let's say, like the first half of data points, and then you see how accurately it predicts the second half of data points. Is that how I'm understanding? Am I understanding it correctly?
Yeah, that's exactly right.
I got it. Okay, and then it's up to you to decide how you split those 2 groups.
Yes, yes.
Okay,
Well,
thank you.
but I mean, I should say that you should split them in a random way. That's important.
Okay, got it. A random way.
Yeah.
Okay, thank you.
I guess along that same lines, how is the random choice determined? Like on how you split it? Like typical practice.
I mean, usually it is just random, like uniformly random sampling.
Okay.
Yeah, where, each data point is equally likely. I mean, you could do more complicated schemes if there's certain, if you have some like rare type events, maybe you want to make sure that you have a few of them both in the training set and in the testing set. So there can be more complicated strategies, but in general, you can just choose them uniformly at random,
Okay.
each of them equally likely. If you have 500 data points and you decide you want to use 300 for your testing data, you can just do that. And of course, there's built-in
Right.
random sampling functions that will just randomly create, okay, use this subset of indices.
Sure. Another question that I had was maybe you covered this and I just missed it, but is it typically an even 50-50 split, or is it like 80-20 or 70-30?
Yeah, it's, in practice, usually more like 70-30, that's kind of a common split.
Okay.
But what people will actually do in practice, well, for example, they might take their data set and maybe divide it into 3 parts, for example, and then take the first 2 parts, train your model, test it on the 3rd part, right? But then also parts 1 and 3 and train, and then test on part 2, and then also take parts 2 and 3, train, and test on part 1. And then that's kind of nice because it takes away some of the like, oh, well, you got unlucky and these data points were in your training set or your testing set because you're using all of the data points in the exact same way. So there's some more kind of complicated strategies that go into this and sort of like, procedure, but.
Okay. Thank you.
Yeah. All right, so let's go ahead and get started again. Yeah, okay, so for the class exercise today, you're going to be looking at a credit data set, and we'll use stats models to study the data set related to credit cards. But first of all, I kind of wanted to go over a few things altogether related to the set and make a few other comments about regression. So the basic idea here is, what are you interested in here in this credit setting? You're interested in your credit limit, which is closely related to your credit rating. And then there's a number of other variables here. So your credit card allows the cardholder to borrow money from the bank to pay for goods and services, but credit cards, of course, always have a limit, the maximum amount you can borrow on your card, which is determined by the bank. And this limit is determined from, various data collected on you, the cardholder, income, age, history, etc., and your credit rating. This is also, of course, important if you want to buy a house or do something like this. So this credit rating is an evaluation of the ability of the card holder to pay back the money, and also the likelihood of the card holder defaulting on the money. Okay, so we will focus on using some regression tools to study this data set. And so ideally, we would like to understand what factors determine credit ratings and credit limits. And this can be thought about from either viewpoint, from the bank's viewpoint of wanting to protect their money, or from your viewpoint of wanting to improve your credit score.
I have a question on linear models versus linear variables. You said earlier that the model is not linear, but it's linear in the model. I was kind of confused about that. Do you remember that?
Oh, I do remember that. Yes. So, yeah, I can go back to that. It was there when we were, I think that the wording here in the lecture is a little not correct when it says we consider the linear model, blah, 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 blah. Because really I would call that a nonlinear model, right? Because it's, but it depends on your viewpoint. Like if you think about, you know, this is X, and sorry, if you think of this as X1 and horsepower squared is X2 and horsepower to the M as XM, you know, if you just sort of associate all those different powers with a new variable, X1, X2 through XM, then it is a linear function of those new variables, X2 through XM, but it is a nonlinear function of the original variable, horsepower. So when we talk about linear and nonlinear, we have to be a little bit clear about linear in what, right? So this model is nonlinear in horsepower, but it is linear in the variables horsepower, horsepower squared, horsepower to the M, right? If you made that substitution, just calling this X1, just calling this X2 and that XM, then in that sense it's linear. So when we say linear, you know, we sort of mean linear in something. But because it's not linear in horsepower, which is what is the first thing to kind of think of in this context, I think it would be more correct to call this a nonlinear model. But we still use these linear regression tools in order to fit the optimal coefficients. But you know, that's like what we did last time when we included the interaction term. So that was a nonlinear model because it wasn't linear in the original variables of the data set. Hopefully that answers your question. I know that that's a little bit confusing.
So that's a series. Would there be an example of a nonlinear? Any series can be considered linear. But would there a nonlinear example?
Well, yeah, I mean, this is, like I said, it depends. When you say nonlinear, do you mean non what? Like horsepower?
I guess that's
this is nonlinear. Yeah, this is nonlinear in horsepower. Yes.
Right, okay.
Yes. Yeah, so I think it's best to call it nonlinear. It's just, you know, it's a little bit arbitrary because you can pull up a data set of variables that are, you have columns that are already there. So you could think about, okay, when I mean linear in the columns that are already there, but you can create new columns by doing various constructions on the original columns. And then if you do like a linear model of your new set of columns, you know, it's linear on that new set of variables, but it's generally nonlinear on the original variables. Okay, so that clarifies it a little bit. I'm happy to chat about that after class or something. But back to the credit data set. Right. Okay, so we get a data set that looks like this, where we have our income, limit, rating, cards, age, education, gender, lots of things. And so we want to summarize and describe the data. That's always a good start. So here we can take a look at what the data types are. Things generally look like what we expected them to be. And then for the categorical variables like gender and student, we can take value counts just to get an idea of the distributions here in the data. It's pretty equally split, male and female. There are a few students, but the majority are non-students. And we also have, a good bit of a majority that are married. And then 3 different ethnic groups represented here. Okay, so you may notice that the income column looks a little odd, 45, 35, 10. So probably we may guess that this is intended to be recorded in thousands. You would think of a mean income around 45,000 as probably reasonable. So we can sort of fix that in the data by applying, just taking that income column and applying a function to it. So we can do the dot map and then define this lambda function to just multiply by 1,000. And that might be handy so that income is in the units that we expect. Okay, so we may want to look at the covariances in the data. So think about how the variables vary together, because this can of course really affect things as you build models with different combinations of them. And so there's kind of 2 ways that you can do this, quantitatively by computing the correlation matrix, and also visually by making scatter plots of the data and looking for patterns of one variable versus the other one. So here we see the correlation matrix. You can kind of just skim through it. It looks like income is highly correlated with limit and rating. Limit and rating are like almost identical. Their correlation is 0.997. So they're almost like exactly the same. Those definitely stand out. You see some strong correlations here with balance and some of these other variables like limit and rating. Okay, so that can be helpful just to kind of glance through and get a sense of it. Cards does not appear to be very correlated with anything. So maybe, maybe that'll mean it's not very useful. And then we can, I guess, usually you want a predictor to be somewhat correlated with your response. It's nice to have predictors, so having variables that aren't correlated with each other, that's not a bad thing. If we want to take a look at the scatter plots, we can. So we can do this with this, this plotting.scatter matrix. So here it'll just take every different pair and make a scatter plot of them. Then you may wonder what it does down the diagonal. And here it's just making a histogram of the variables. So here's a histogram of income, limit, etc. Okay, and then this is, again, just kind of reinforces what you can kind of see in the correlation matrix. It's useful to take a look at this, though, because you might discover a nonlinear pattern or relationship between some of your variables that you couldn't see in the correlation matrix. And you can, get a sense of which ones are strongly correlated. You do see some weird kind of lines going on here. Any guesses as to what's causing this weird sort of looking plot in some of these subplots?
I would guess because they're discrete, you can't have half a card or a third of a card. You only have integer quantities of cards.
Yeah, exactly. So that's exactly right. Yeah, some of these variables take on a discrete set of numbers, and so you're going to see these jumps in those plots. Okay. Right. So this is useful for exploring patterns and relationships between the quantitative variables, but we weren't able to do anything with the categorical variables. So one thing I wanted to mention was how you can try to do some exploratory related to categorical variables. And one real simple thing that you can do is side-by-side box plots. I don't know if you're familiar with box plots, but I'll show you a picture here in a second. This code is first just making bar plots. The bar plots are just the value counts of the variable, so you can kind of see the distribution, as we already discussed, male versus female, student versus non-student. But this doesn't really get at any kind of, is there a relationship with the response variable that you're interested in? So for that, it can be useful to make a side-by-side box plot. So here you're looking at credit limit, and then you're looking at the values for the males and for the females, and for the students and the non-students. And this, what a box plot does is it plots the median or the 50th percentile in green, and then it plots the 25th percentile and the 75th percentile, the quartile here. And then it sort of does these little whiskers out to your non-outlier points, and then we'll kind of mark the outliers with individual dots. So it's just kind of a quick visual summary of the distribution, but you can glance at this to kind of see, oh, do we see significant differences for males, students and non-students, etc. Okay, and this is how you would actually do it. So first you sort of define your subplots like you were doing in your last homework. And then you can do a dot box plot, and you just need to specify, the variable that you want to plot and use the by functionality to by different values of a categorical variable. Okay, and this is making those 4 plots. Okay. All right, so I would just glancing at these plots, it doesn't like stand out to me that, oh, wow, we see a really big difference between, some of these groups in terms of credit limit. But in other cases, you might see a really strong relationship, and it can be very helpful to incorporate categorical variables into regression models. But how do you do that? How do you incorporate a categorical variable that's not a number into a regression model? It's easiest to do if the categorical variable is binary, like gender, male, female, student, yes, no, married, yes, no. Those are a little bit easier to deal with. So how would we do that? If we just have 2 categories, male and female, then we can create a dummy variable, which turns gender into a number. So we can just define a new variable, gender num, which is 1 if female and 0 if male. And then we can explicitly incorporate this into our model. And so you can see here what will happen if you run a regression model trying to predict income just from gender. As you might guess, that does not go so well. So there's not a strong relationship. You get an R squared of 0, and you get this coefficient on gender is very large. Okay. But what you'll do in your activity, so you're going to kind of build a regression model for that data set. And then one of the things that you'll look at is, are any of the categorical variables in the data set helpful? And then just to mention one other thing before we do, if you have 3 categories like the ethnicity variable, you can also encode that into a linear regression. So the general procedure for that would be that you need 2 dummy variables to encode a categorical variable with 3 values. So here, ethnicity, you could say it has 3 different values: Caucasian, Asian, African American. You do not want to say 0, 1, and 2. That would be a very bad idea. Because you don't want to say that, that Caucasian is further away from African American than Asian. You don't necessarily have a clear order associated with your categories, so you don't want to just assign an order here. So the correct way to do that would be to use 2 dummy variables. So you can define a variable that is basically a yes, no on, is somebody Asian? So Asian, yes, no, 1 if the person is Asian, 0 otherwise, and yes, no. And then you can actually only need 2 of these variables because if if there's 3 possibles, then if it's 0 Asian and 0 Caucasian, then you can infer that it has to be a 1 for African American. So you in fact wouldn't need 3 dummy variables here. You would just need 2, because you would encode Asian as 1, 0, Caucasian as 0, 1, and African American as 0, 0. Okay, so, and then we have a question. So if you have in ethnicities, you would make n-1 dummy variables. So let's think about this for a second. If we had, I think that that's the right way to think about it. So we can think about if we had a 4th category here and we had 0, 1, 2, and 3, exactly, then you would not need the last one. Yep.
Wouldn't the number of dummy variables be the degrees of freedom?
The degrees of freedom? What do you mean by the degrees of freedom in this?
Well, like you said, if you know the first 2, then you know the 3rd one. So there's only 2 degrees of freedom in the 3 genders, but that might not be the same with every type of category.
Yeah, I mean, it's true. It might not be the same with every type. So by degrees of freedom here, I'm assuming you're meaning like number of categories, something like that?
Well, in the ethnicity, and they're all independent. If there's 3 ethnicities, then there's only 2 degrees of freedom. Because if we know one of the first 2, we'd confer the last one. So that's not a degree of freedom. Does that make sense? I guess not.
I don't think I'm following exactly what you're trying to say. I guess usually, are you saying that you think it would be a different number, like if you had in categories for your variable, that you wouldn't need n-1 dummy variables to encode that uniquely?
It depends on the variable. In this case, yeah, but I think there might be some where you need fewer.
Um,
Is it correct to use degrees of freedom for this case?
I wouldn't use that term here.
Thank you.
I mean, I can see where that's coming from, because it's sort of like, oh, you know, then that last value is determined. So I can see that, but it's not sort of, I don't think that that's what people would normally refer to as degrees of freedom. Okay. So what, okay, well, let me try to wrap this up soon so you have some time for your activity. Just wanted to mention that there's the get dummies function, which can automatically create dummy variables for you. Actually, if you do, it just makes one for each ethnicity. So it just turns those into a yes, no for each ethnicity. But then if you're actually running the regression, you would only need to include any two of those three. Okay. So let's stop there and go ahead and do our breakout groups for the last few minutes of class, so you can play a little bit with some of this stuff. Any other questions before we get that started? Okay, excellent. So let me, all right, so I'll go ahead and start the rooms, and then I'll close them out at 1:45. I'm happy to answer a question or two after that, though, if people get stuck on anything. All right, have fun.
Hi, I have a couple questions.
Yeah. Hi.
So when you were talking about a linear regression with categorical, so you assign a 0 or a 1,
Mm-hmm.
how does that differ from a logistic regression?
Oh, excellent question. So what about is using a 0 or 1 as your predictor. In logistic regression, you're using like 0 or 1 as your response. So in logistic regression, it's the Y categorical. This context, it's one of the X's that's categorical, but the Y that we're predicting is still quantitative. And that's the difference.
That makes
So
sense.
when people say regression, they mean the Y is quantitative. When they say logistic regression, they mean the Y is categorical.
Okay, thank you. That helps. I had another question. It wasn't related to this. So I guess if there's anyone else who has a question related to this, I'll let them ask first. Okay.
No, I think you can ask. Go ahead.
Okay, so for the homework, we had to calculate a z-score. And then from there, we had to calculate a p-value. I guess I don't quite understand how to calculate a p-value. Don't you usually use like a table for like the z-score, and then you like find the p-value?
Yeah, there's different ways to do it. So a lot of textbooks will include these big tables where you can look up the p-value from the z-value. And that's basically because we didn't used to have like calculators and computers, that could just compute them for us. So I guess that's a little less common now, but it's still, yeah, it's a valid way to do it. Basically, you think of the z-value as a value in the standard normal distribution, and then you're trying to compute the area and the tail cut out by that value. So if you had a z-value of like, I don't know, -3, then you want to compute what's the area in a standard normal distribution from -infinity to -3. You can the lookup table, or you can just do that using the normal CDF function in Python. And also for the homework, you could also just use the built-in hypothesis test in Python to compute it too. So those are all valid ways.
Okay. That sounds good.
For the homework, you want to do it without the lookup table because you want to do it
Yeah.
like some kind of way in Python. Yeah.
Yeah. I guess I understand the concepts, but Python is holding me back from doing great on the homework. Not the
Well,
best.
I imagine it's like a steeper learning curve at the beginning, and then hopefully it will get less frustrating as it becomes more familiar.
Okay. So you said there was a CDF function, and then there's a built-in hypothesis test function, and those can help calculate.
Yeah, those are like two different ways that you can do it. If you look back at the lecture 7, yeah, lecture 7 is where we did that. But there's examples there of the norm CDF, you know, how you can compute a p-value with the norm.cdf function, and also at the end we did an example of just doing the 2-sample t-test and the 2-sample z-test for proportions, how to do the code for that.
Okay, that sounds good. Thank you.
May I ask about some questions about the homework?
Yeah, sure.
I don't know if this is allowed to ask, but I just want to check for the null hypothesis and alternative hypothesis for 2.1. So what I have written is that null hypothesis is the proportion of clicks on logo A and the proportion of clicks on logo B are the same. Is that kind of correct, or is that like totally off?
Oh, hold on one second. Let me end the live streaming.
Okay.